include some lines. If not, Miss Lee will be all over the place. Right, so this is a review session for chapter 25 and 26, which is quantum. All right. This entire topic, right, especially quantum, chapter 25, is very fact heavy. So it's quite a factual topic. Meaning to say, if it's the kind of topic where if you study and you understand, then it's relatively manageable. But if you don't, then it's like legit don't know what to write. Okay. So for quantum, right, I'm going to draw like kind of like a mini mind map. So the first thing we look at is photoelectric effect. And I think for quantum and nuclear, you will expect 2 to 3 questions. So here in this group, we are talking about anywhere between 18 marks to 24 marks, depending on your luck lah. Don't know. I don't know. Plus minus 2 marks. Okay. So this is about, again, those of you who join the morning session, this is about 20% of your paper 4. This paper, this question, very hard to be tricky. Because how? All right, we're going to start first with the first one. The first one, or the first section of the question would be about wave-particle duality. Is this thing a particle? Is this thing a wave? Which is the whole problem about quantum physics to begin with, right? For classical physics, which is every other chapter before chapter 25, things were kind of normal. We look at something, we know whether it's wave, we know whether it's particle. But quantum, we don't know. Okay, so the first thing we need to talk about is the photoelectric effect. All right, so again, if you hear some thunder, some lightning, it's because raining outside lah, huh? It was very much louder just now. And then halfway my house, like after I go offline, is the circuit lah, okay? The power box trip. I'll be back. Don't worry. Anyway, photoelectric effect, okay? The photoelectric effect, you must know what it is, lor. Okay, which is the emission of photoelectron from a metal surface. Okay, go and look at the notes. My notes very little already. You go and open your textbook, it's like 4 or 5 pages of essay. All right, so it's the emission of photoelectron from a metal surface due to incident electromagnetic radiation. I find just drawing stuff as a student quite calming. It's a revision session for my own brain. So when the electron gets out, okay, it needs energy to escape. This energy to escape is known as work function. Okay, so you need to know, number one, what is photoelectric effect? So what is this one? Define this. Second thing you need to know is what is work function. Okay, definition, minimum energy required for electron to be released from the metal surface when incident EM radiation hits the metal. So this photon will reach the electron, give it some energy, the electron receive the energy and jump out of the metal surface. That is photoelectric effect. So here, this work function is HF naught or HC over lambda naught. F naught here is known as threshold frequency. Threshold frequency. Lambda naught here is threshold wavelength. Right? So you need to be able to define work function. The second part is once the electron is out, or let's say now the electron is here, it will have a certain amount of kinetic energy. Right? So some electron will travel faster, some electron will travel slower. If you need a visual on this, there are certain seams that Miss Ellie and I will have already been shown in the recording. So different kinetic energy. But let's say this is the maximum kinetic energy. Work function is the minimum energy to escape for electron to escape metal surface. This is a short form one. Please go look up the full one. Okay. So if I want to find the maximum KE, I can put it all together and say that using conservation of energy of photon is equal to work function minimum energy to come out the metal surface plus Ke max. Okay, a lot of discussion has been recorded regarding this. So if you need to, you can watch this, but if it's like too close to paper, what you should do is you should try to memorize the equation and use it in different questions, which we will do following this. Okay, so we need to be able to, definition, I'm going to highlight, okay, what you need to know how to define, meaning they can ask lah. Look, definition is 2 marks here, 2 marks there. You keep losing 2 marks here, 2 marks there. Very pain leh. So take some effort to memorize. No? Define photoelectric effect. Define work function. Define threshold frequency and threshold wavelength. Okay. Also, remember that why this have a range of kinetic energy. The short answer would be the electron, some of them is beneath. It's not on the top layer. They need a bit more energy. So because they need a bit more energy, what is left behind for them is less. But we look at this one. This is the main equation. Okay, auxiliary equation, meaning just because you know this equation doesn't mean you can use it. We need some additional equation like side dishes. Okay, so the first auxiliary equation is the energy of photon. Okay, energy of photon. Photon is light particle. So this one will be equal to hc over lambda or hf. Again, confirm you will use this equation in your A21. Just don't know whether they ask hydrogen spectrum or photoelectric effect or de Broglie. If they all three never ask, then it's not a very balanced paper lah. Okay, so the first auxiliary equation is this one. The second auxiliary equation, or the second equation that you should know, is kinetic energy. Maximum kinetic energy is E stopping potential. Okay, so CIE is a bit cold in this regard. This relationship is in your syllabus, but for some reason the past year didn't ask a lot lah. Doesn't mean it won't ask. Okay, so here is stopping potential. This came out in your trial already, which is the potential needed to stop the fastest, the most energetic electron. So sometimes we need to put this one into the equation to find stuff lah. So questions that they will ask regarding this will include a graph. Most of the time it will include graph. And the second thing is they can ask you to determine if any electrons are emitted. So we will have to use the work function test. All right. So these are the main, the main two classes of questions that they will ask just solely on photoelectric effect. Okay, there are many graphs we can draw. I will probably choose one or two to discuss, maybe just one. You should familiarize, you should know how to linearize. If you don't know how to linearize graphs, please fix this problem by watching the linearizing video already recorded. Because if you don't know how to linearize graph, it will affect any kind of physics question with straight line graph, including paper 5. You want to burn 2 questions in paper 5, 30 marks because you don't know how to change, you don't know how to y equal mx plus c, give you bonus you don't want. So please learn how to linearize. If you don't know, you really don't know, ask your teachers, okay? Ask me, ask Miss Ellie, ask any one of us lah. Right? If you don't know how to linearize, it's very stress one because confirms paper 5 will ask. So it's worth it. Make sure this skill is okay. All right. I think this is, and another one that sometimes if come out, then not sure how you feel about it, which is the how the experiment observation. Experiment observation leading us to conclude that light has particle behavior. Okay, so just very quickly, okay, I'm not going to explain. You can watch the video for explanation. But we know light has particle behavior because the emission of photoelectrons are instantaneous. You shine light, immediately the electron come out. No need to wait. Okay, in the continuous energy world that you and I live in or observe, this doesn't happen. correct? If let's say you want to boil water to make Maggie mee, you have to wait, right? So you want the electron to come out, you also have to wait for the electron to receive energy. No, this one is you shine light, immediately electron come out. No need to wait. Okay? And then what else? The rate of emission of photoelectrons depends on intensity of EM radiation. Okay? The maximum kinetic energy of the emitted photons, photoelectrons, the electron. If you write photoelectron and it confuses you, then don't write photo. Photoelectrons are the electrons that come out from this photoelectric effect because it's light ma. Electron that came from light, photoelectron. If you confuse photoelectron and photon is light particle. Okay, so if you're confused between these two terms, don't use photoelectron, just use electron. Okay, photon, then you reserve photon for the light particle. Okay, so the maximum Ke of the electron only depends on the frequency incident photon. This is also the okay. So once again, if you need a bit more understanding for you to write this explanation with more conviction, go and watch the video. Okay, so photon is the one that is incoming. The light that is incoming. This is photon. The electron that come out because they receive energy is called photoelectron. You don't want to write photo also can. All right. So linearize the graph is important and then writing the experimental observation. The fourth and final thing that you should know is to explain the effect of changing intensity or frequency of photon. Okay, so I want to start by showing you a question like part 4. Because that one very recently came out one. That would be from the year. Okay, so we're going to do some examples now. ON19 paper 41. Question 11. Okay, it is already probably discussed and recorded already. Okay, because I think we have chosen the example. So I'm just going to show you the question now. Okay, so this question, right, we are dealing with just the photoelectric effect, no combination with other parts of the chapter. Okay, so I'm gonna speed run through this with little explanation. But if you have done this, then just treat this as revision, no? Revise ma, review ma. Already view before, we come back and view again, review. Right. Okay, so what is meant by work function energy? This one would be the minimum energy of incident photon 1 mark for electrons to be emitted from metal surface. Should mention metal surface. Okay. Next, we are given the work function energy, which is this much in joule. Very good. So just FYI, when you use this equation, this energy that you find if you use this Hc over lambda, this energy is in joule. But sometimes they will give you in eVolt. So make sure you know how to convert to eVolt. So basically, just because you know this equation, but you don't know how to do all these things, you also cannot really do the question one. Does that make sense? So make sure you know how to convert. You go to eVolt, you multiply by electronic charge, go back to joule, divide by electronic charge. So all these side dishes, side things also you need to know. All right. So from here, you are asked to calculate the photon energy because we have a EM radiation of 280 nanometer. So E is hc over lambda. Okay, Planck constant can be found from the front page, -34, 3 times 10 to the power 8. So this is what I mean by confirm we'll use one, just don't know where only. X-ray can, anywhere also can. So I'm going to press my calculator, or actually, ding, ding, ding. This one is 4-1. I'll just open the mark scheme lah, so that I can tell you what are the important workings to show. In a sec. You can press your calculator first. Okay, so this one is 7.1 times 10 to the power of -19. Okay, this is a very straightforward mark. If you are last minute study, exam panic, you don't know what you're doing with your A2 life, you just want to get this over with. These are the marks that you can get easily lah. But substitution and leading to answer is A1. Writing this equation is C1 already. Don't let it go. Take the mark. Okay. Find the maximum speed of the electron emitted from the metal surface. So this one, we need to use the whole Einstein equation. Energy of photon is equal to work function. Right. If writing the equation in word form, that will help you, can, plus Ke max. So we know the energy of the photon, 7.1 times 10 to the power -19. We are given the work function, 5.5 times 10 to the power of -19. Okay, if you want to find, I will normally just find Ke max first, but this is good enough. So you can see this 7.1 is more than enough to kick the electron out, because to release the electron, you only need 5.5. Okay, so here I will just put bracket 7.1 minus 5.5 times 10 to the power -19. Everybody is in joule, so this is pretty good. Ke max, okay, we are talking about electrons, so find the mass of the electron, 9.11 times 10 to the power of -31 kg. In the front page of your data booklet, V square, half mv square. Okay, all these equations you should know by now. And finally, you should get your value of V, 5.9 times 10 to the power of 5. Please always think about, does this number make sense? Okay, it makes sense because it's very fast. But if it's faster than the speed of light, then it's wrong. You didn't convert something. Or if it's too slow, like 59 meter per second, cannot lah. All right, explain why most of the emitted electrons have lower speed than Vmax. Well, this is because some electrons are below the metal surface. Because of this, energy is required to bring the electron to the surface in addition to the work function. So your electron, let's say you got one electron at the surface, one electron down here. For this electron to escape is easy. I need 5.5 times 10 to the power -19. So if you give me 7.1, I am happy because the electrons that come out, let's say the electron that exit the metal surface here, it will have the kinetic energy of 7.1 minus 5.5 times 10 to the power -19. Very nice. But let's say another photon is sent to this electron. This electron needs some energy to get to the surface. I don't know lah. This is the extra energy. So when I say in addition, I mean this one. I need the extra energy plus 5.5 times 10 to the power negative 19. Meaning when this electron escape to the metal surface, the kinetic energy is equal to 7.1 minus 5.5 minus whatever this extra energy is. So your energy is less already. So the whole idea of range in Ke, lower speeds, is because the electrons are below the surface. Okay, so we need energy to bring the electron to the surface first. Then we can go through the process of work function plus Ke max. Okay, so the last part here is the explanation that I'm talking to you about. But here you are asked to fill in a table lah. Sometimes they will just give you the situation and you explain in words. All right. So here we can change intensity or we change frequency. So whenever we change intensity, we are changing the total energy. Okay, when we change frequency, we are changing the size of the photon. Because E is equal to HF ma. So higher frequency, it means more photon size, means the 7.1 become bigger. So if we reduce intensity at constant frequency, this means our total energy is less. So, but the size of the photon is the same. So now this one means less photon, but same energy. So if we have less photons, right, we will have less electron. So this one will decrease. You don't have that many photon. So maybe instead of giving you 2 photon per second, I only give you 1. So GG, one of these electron won't have any energy. Sad. Okay. But the maximum speed is no change. No change because this maximum speed only depends on frequency of photon. Remember our observation, this is one of them. The Ke max or the maximum speed only depends on the frequency of the photon. This means when we increase frequency, this maximum speed will increase. Okay, because this one, more energy. But important part here, they say constant intensity means the total energy is the same. Same total energy. If we have the same total energy, but each photon is going to whack more energy, then now we will have less photon. Less photons? Yeah. Because right now, your total energy is the same, but each photon go take more energy. We can only make less energy now. So this one decrease. Okay, so less photon because each photon has more energy. But total energy the same. Hence, less photon can be made. Okay, there are many analogies we can use to discuss this, but in the benefit of finishing the recording under 2 hours, go and think about it. There are many examples where Miss Ellie and I go explain this in various different formats lah. All right. So this is the whole bulk of it. In the trial paper, we gave you a graph, but I was a bit mean lah. I chose a non-linear graph without telling you it's a non-linear graph. But if I'm looking at past year, it feels like the graph has not made its appearance for a while. Let me double check. Very interesting. If they have, we will do it from ON. Do we have? Oh yes, we have one from ON. Okay, we'll do the one from ON. ON20 paper 4. Okay, and it's a very different question in nature. So for this one, yeah, I'm gonna This is question 11. Okay, you think about what to write here. The two other observations. So this is what I mean by the experimental observation to show that light behave like particles. Okay, and this one is bigger, so we can stare at the graph with great conviction. So now, if you are struggling in physics, look, if you're not struggling in physics, it doesn't really matter what question come out. You may have certain weaknesses, you may struggle with memorizing definition, writing examples, but seldom you struggle with calculation one lah, or the main ideas of physics. Then you know what to sharpen. But if let's say you really just want to make sure your grade doesn't tank, then my suggestion is identify the questions that you find easy. Like this kind of linear one, I think they are quite easy. Because what can they ask you? Gradient y-intercept easy. No change in flux, no differentiation, easy. Okay, anyway, here, EM radiation is incident on a metal surface. It is observed that there is a minimum frequency below which, oh, this is threshold frequency. That is actually the fourth observation. Hang on. Did I type it out? No. Okay, I add. Don't worry, this one I will send to you later. So this one is the existence of a minimum threshold frequency. Cannot spell well. Elections, yes. Below which no electrons will be emitted from metal surface. Okay, so 1, 2, 3, 4. Yes. Let me zoom this one. Ding, ding, ding. Okay. Next. So what other observations can you write? Two other observations to show the particulate nature of electromagnetic radiation. You can talk about the maximum speed and maximum Ke, only dependent on frequency. You could also say that the frequency affects the speed, the intensity affects the rate of emission of photoelectron. Okay, or you could talk about the time delay. So I'm just going to show you the mark scheme. Okay, just make sure you don't repeat the thing that they say here lah. So either maximum Ke doesn't depend on intensity or maximum Ke depends on frequency. I think these 2 points are the same point lah, but well, if they think that they're different, then okay lah. And also there is no time delay between photon incident and emission. But I caution that you also write the bracket, okay? Although it's inside the bracket, because inside the mark scheme, if they say no time delay, if I'm an examiner and I'm like, no time delay between what? You writing and you thinking? So try to write either between illumination and emission, or you want to write a bit more between the incident EM wave or EM photon and emission of photoelectron. All right. Anyway, the maximum Ke emitted from a metal surface and 1 over lambda graph is here. Okay. Pro tip, you see all this, you better circle and you know, like, oh, remember, okay, this is E volt and then this is 10 to the power of 6. Don't make mistakes already, these kind of mistakes. All right. So we are asked to find the threshold frequency. So sometimes our students get very stuck one. Why got Emax here, 1 over lambda, then got frequency? I am confusion. Okay, whenever you see this, you always start with the energy of photon equation. Okay, the conservation of energy equation. Energy of photon is equal to work function plus Ke max. In this case, they call it Emax lah. Whatever, don't care. All right, this is Emax. This wavelength lambda here is the wavelength of the EM radiation. So it is the wavelength of this photon. So this one, I can rewrite this as E is equal to hc over lambda. Work function plus Emax. Now you hold on to your horses first. I know you're very excited and you want to rearrange. But how do we find threshold frequency? Threshold frequency is related to minimum frequency, which is related to work function. So you think, okay, work function is hf0. Should I substitute here? Up to you. You can. Maybe I shall do that. hf0 plus Emax. I will rearrange what is on my y-axis. Y-axis is Emax. So in the effort to preserve the y equal to mx plus c format, I will rearrange. This will be hc multiplied by 1 over lambda minus hf0. So you see, this is y is equal to mx plus c. So you can see here that your gradient m is equal to hc, and your y-intercept is equal to hf0 negative. But we got some problem here lah. Because in part 2, you're asked to find h. So it's not very safe to use h here. And can you even find the y-intercept? No. Your miss very stressed. Cannot find y-intercept. How? Have you forgotten the other intercept, which is called the x-intercept? Okay. So since y-intercept is not helpful, don't worry. We are going to use it later. Okay. So we are going to continue here, and then we will find the x-intercept. You want to find the x-intercept, you will let the y-axis be 0. Right? So let Emax, the y-axis, be 0. So if y-axis is 0, 0 is equal to hc 1 over lambda minus hf0. The h and h can cancel, right? Because I divide everything by h. Okay, I'll carry this over. f0 is equal to c bracket 1 over lambda. Okay. So this will be your x-intercept, because 1 over lambda is your x-axis ma. So go find what is x-axis. Hiya, we need a straight line or a ruler. I don't have. This is going to take forever. Hang on. No, not forever. I'm just an impatient person. Okay, line. Let's draw a straight line. Wow, it's like one note know that I have a long semester. Okay, it was fairly cooperative. Okay, so hopefully yours is better than mine. You draw your y-intercept, and I'm going to cheat a bit and stare at the mark scheme. It is 1.93. Okay, 1.91. Yep. 1.93 times 10 to the power of 6. Okay, what is that? So from here, f0 will be equal to c is the speed of light, 3 times 10 to the power of 8. 1 over lambda is 1.93 times 10 to the power of 6. Okay, press calculator. And finally, we will get f0 as 5.8 times 10 to the power of 14 Hertz. So this linearizing thing you can do, or you can just immediately sub Emax as 0. Okay. So when Emax is 0, 1 over lambda is equal to f0 over c. And then you can find this one and put inside. All right, so just be mindful that right now, your y looks different lor. Your x looks different lor. But you can just treat this as a single thing. Compartmentalize, okay? Use the gradient to determine the value of Planck constant. Okay, anyway, the marks for this one, answer is 1 mark, A1. And You put Emax as 0 here. This is C1. And then you read the y-intercept leading to this one. So basically, we need to see 1 over lambda is equal to 1.93 times 10 to the power of 6. Or your x-intercept or something like this. We need to see you do this reading plus the straight line. So we will check your graph as well. Okay. All right, next, use the gradient of... So what we learned here is, sorry, I come back again. X-intercept is as important as the y-intercept. All right, so you have 3 options: gradient, y-intercept, x-intercept. If you stress, finish the paper, come back and slowly stare at the equation. All right, use the gradient in the line to find the value of Planck's constant. Well, we already linearized there, so no need to bother already. Just write gradient is equal to hc. If you want to, you repeat this one again, or hc over lambda is work function plus Emax. Or you write the equation. I'll write the equation. Because I didn't use it just now. So I'm just going to write this here. Something like this. Okay. So later I will explain a bit, but this one here will have 1 mark C1 that belongs here. So writing here, as long as within the same question part B is okay, we can still give you mark 1. But you better make sure you write big and clear lah. If your writing is all over the place and examiner cannot find, I also cannot help you already. Okay, so you either transfer, you want to play it safe, you transfer this over, you write another form here so that the examiner know what you're talking about. But leading to HC is gradient, this is C1. Okay, so now we find the gradient. I'm not going to spend too much time finding the gradient. Working is needed, if not, you will not get marks. All right, so to find the gradient, right, we'll take 2 coordinates from the graph. You like lah, which coordinate you want to take? Maybe I take this one lah. Because this one looks like a part that passes the point here. Okay, let's take this one. 2.3 times 10 to the power of 6, comma. Extrapolate here, this one is 3 boxes, 0.46 eVolt. 2, 4, 6, 8, 10. Yes, 2.3, 0.46. So the gradient here would be 0.46 minus, I put 0 lah, okay. And then this one would be 2.3 minus 1.93. 2.30 minus 1.93 times 10 to the power of 6. Okay, I'm going to kidnap this and bring this over. Note that this one is in eVolt. So because this is in eVolt, we need to convert first. So this will be 0.46 times 1.6 times 10 to the power of negative 19, right? Divided by 2.3. 2.3 minus 1.93, 0.37 times 10 to the power of 6. We're looking for Planck constant. C is 3 times 10 to the power of 8. Then you can find your H law. Okay, let me see if my answer is within the range, because I use a different coordinate than the mark scheme to show you that it doesn't matter as long as you read properly lah. 0.37 times 10 to the power of 6. Okay. So I got exactly 6.63063. Okay, not good enough. Times 10 to the power of negative 34. 4 marks. Where are the marks? Okay, so 1 mark is the equation. Energy of photon is equal to work function plus Emax, or Hc over lambda is equal to work function plus Emax, or some form of this one lah. Okay, this is C1. C1, another C1 is Hc is equal to gradient. All right, you find gradient with the correct coordinate and conversion. Here is M1. So finding the gradient plus conversion. You need to show this. If you don't show this, you will not get the final A1 mark for the answer. And you also need to show this. This 2 is A1. You skip too much step, you could get 2 out of 4. Okay, working is needed for this whole thing. So just, especially those who like to skip steps lah. Don't skip lah. Nah. So again, I'm gonna move this down a bit. Nah. So the working is needed. The working and answer is needed. So you can see this is their Y1, their Y2 minus Y1. This is E volt to joule. This is X2 minus X1. Whenever you are using gradient, whether it's paper 4 or paper 5, please show this. Don't be lazy. If you don't show, then they can say, I didn't see the working, 0. Oh, I've forgotten. I'm not going to crop again. This is C1. C1, you don't show, can have leniency. M1 is must show. If your M1 is 0, then it will be A0. Then this A1 will not get marked. So this 2 is link 1. Okay. So after that, you multiply by the HC like this, also can. Then you get A1. Again, working and answer is needed. Be very careful, especially when you have a 4-mark part, when they ask you to find stuff from the graph. Okay. Finally, the EM radiation have a larger work function. Oh, larger work function. Sketch the variation of 1 over lambda or Emax. Okay, so let's go back to this thing and we think a bit. If it's larger work function, or rather I'm a bit sprained, but this thing, y-intercept is negative HF naught, right? And negative HF naught is negative work function. So if I think from the perspective of the graph, okay, let me just try to find space to draw the graph here. The graph of Emax against 1 over lambda is a straight line graph, right? With the y-intercept down here, dot, 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 like that. So if I have a larger work function, it means that my y-intercept will have a larger number, larger magnitude. That means it will be down here, dot, 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 bloop. So this one here, larger work function. So it's a bigger negative phi. Okay, and these 2 lines have to be parallel. Why parallel, you ask? Because did you change your gradient? Did you change your H? No, Planck constant is the same. Did we change the speed of light? Well, as your God, no, none of us can change the speed of light. So the gradient is constant. All right. So now I need to draw a line that is beneath the original line. That is parallel. Anywhere lah, can already done. Okay, anywhere doesn't matter. So the 2 mark here, the first mark is for you when you have a same gradient as the original. And the second mark is when your x-intercept is greater than 1.93. Anywhere, doesn't matter. Unless they give you numbers, then you have to calculate. They didn't give numbers, draw anywhere you want. as long as it's parallel. You just take your ruler and then you gap one ruler and draw one line and then call it a day. Wow, physics so nice. One line, 2 marks. Okay, whether you draw the correct line. Also, they are very nice for you. You legit, you look at this. If I'm a student, I don't know whether I want to draw on top or below, but I know it's parallel. Then how can you draw on top? There's no space. I mean, you can, but the likelihood is here. Okay, if you want to guess. Try not to guess. Try to actually think it through. All right? But if you're running out of time, like you, I don't know, fell asleep halfway and didn't finish the paper, and then you're like, oh no, I need to sketch this. Quickly draw one line parallel. Okay? Either higher, larger lambda or smaller lambda. So for this one, the work function increase. So work function increase. Now, work function is hc over lambda naught. Work function hc over lambda naught. Did it work function increase? Larger work function energy. If you use this, then you a bit stressed one, because you notice when you use this, when this one increase, this one cannot use this one, okay? Don't use this, do not use this. Use the equation that is linearized, because other things are constant, and other things are also changing. So you need to consider the energy of the photon as well. The energy of the photon is staying the same. So how would it affect the graph? Okay, so don't use this. Don't use this. Use the linearized form. Okay. The way I use the linearized form is to look at the y-intercept. Because the x-intercept one, then you need to substitute and then re-evaluate. Because something happened here to the x-intercept. If you check here also can, but I generally find it easier to check here. So the y-intercept will be bigger in magnitude. So if I want a larger y-intercept, there's a larger negative number, I will draw it below the original line. Larger y-intercept below the original line, because the work function increase. And work function is y-intercept. Okay, that's it for the photoelectric effect that has just the photoelectric effect. But photoelectric effect doesn't stand alone. It also have the de-Broglie equation and wavelength. So lambda is h over p. So we have the photoelectric effect where E is equal to hc over lambda. So when we have this lambda and this lambda, we can have all sorts of funny question involving some electron deflection, some funny equation like force or pressure exerted by the light on a piece of paper. And also, if you just want the de-Broglie or the de-Broglie equation one, then we will look at momentum of the light or wavelength of electron. Important auxiliary equation that you should know is this P. By the way, this P here is momentum, okay, not power. Okay, so an important equation that you should know is sometimes we can find the speed of the electron, because momentum P is mv. So we can find the speed of the electron using half mv square is electronic charge eV. Here you see, Ke max is eV. Half mv square is eV. So for this one, these are what I mean by auxiliary equation. Later you don't know, then you can't solve the main part, which is this two. All right, so this is another type of question. Something like this came out in the other paper variant of ON20. Let's do that one. ON20 paper 4241. Again, question 11. Pretty cool. You get 10 marks. So this is a combination one. They should ask at one of these because these are actually very groundbreaking effect that all physicists should know lah. So very rarely they don't ask one. They will ask some version of photoelectric effect or photon, or they'll ask some version of de-Broglie wavelength. Or they will try to shoehorn it inside something like hydrogen spectrum. Okay, anything else? Did I miss some stuff? I think I did. Oh, this is a 9-mark question. Very nice. Okay, so this is an example of the de-Broglie relationship question. Okay, so we're gonna look at this is what we call an electron deflection, because you shoot a light particle at the electron and then for no reason the electron pew it gets knocked off. It's like you are just chilling there, just chilling, minding your own business, and then a light particle come and whack the electron, then the electron come down. Why? Okay, anyway, we got the wavelength of the photon. And then after you deflect, oh, the wavelength decrease one. GG, what happened? Okay, anyway, let's state what is meant by photon first. Okay, photon is a quantum physics. Quantum means it's a fixed amount. Okay, those of you who do economics, we use quantum in econs also, right? A fixed amount. Okay, so it's a quantum. That means fixed amount that is associated to wavelength one. Quantum of energy of EM, electromagnetic radiation. And then you can write hc over lambda. So different wavelength will have different energy. Draw an arrow to show where the electron will go. Hiya, this one got shoot downwards. You hit the electron downwards, the electron will go upwards, right? Okay, so somewhere like that. Don't know where, doesn't matter. It looks a lot like the oblique collision in AS. All right, calculate the momentum of the deflected photon. Ooh, I know. de-Broglie wavelength is Planck constant over momentum. Momentum is Planck constant over wavelength. So 6.63 times 10 to the power negative 34. They say deflected photon. Please use 544, okay? Don't use 540. If you use 540, then you didn't read question, not set. Please read the question. 544 for deflected photon. 544 times 10 to the power of negative 9. Nano. Goes without saying, if you don't know your prefix, also please remedy that. If not, do better. Not very hard to do physics already if you don't know prefix by today. Do better. You got this. Okay. Wow, 2 mark. Miss, where is the mark? Yeah, very nice one. Quantum. You write equation, you get 1 mark. Okay, substitution leading to the final answer is A1. You don't write the equation and immediately go write the answer. Please show the substitution. Without substitution, I can choose not to give you A1 marks, okay? Energy transferred to the deflected photon. So we can find the change in energy of the photon, right? Energy of photon. So the del E will be hc over lambda for the deflected photon minus hc over lambda for the incident photon. Okay. Let's factorize the hc. 6.63 times 10 to the power negative 34. 3 times 10 to the power of 8. 1 over deflected one is 544 times 10 to the power negative 9 minus 1 over incident is 540. Okay. 540 times 10 to the power of negative 9. So if we press our good old friend, the calculator, we should get 2.7 times 10 to the power of negative 21 joule. Right. This one, if you minus, you will get a negative lah. You want to keep the negative also can, but the negative here shows that the negative shows us that the energy of the photon decrease, and then it is transferred to the electron. Okay, so the photon, which is represented by these squiggly lines, now wave is just wave particle. Okay, so imagine it's just another particle whacking this one, and then this particle come here. This particle got less energy, so when I take final energy minus initial energy, I will get negative. So this one will take some of that energy away. Okay, so here energy of photon decreases, is transferred to the electron. You can just write the magnitude. All right, next part. Another photon of the same wavelength 540 collide with an isolated stationary electron. Explain why it is not possible for the photon to have wavelength less than 540. Like for example, 544 is greater than 540. Of course cannot lah. Because if you have wavelength less than 540, it means that the deflected photon must have more energy. Cannot lah, because we cannot create more energy. So I would say that the deflected photon must always have less energy after collision. Okay. Since greater wavelength, smaller wavelength, less wavelength, since smaller wavelength means greater energy, it is not possible. Impossible. Okay, so you mentioned the deflected photon must have less energy after collision, or it loses energy. Okay, addition marks. So this is good enough already. You can get full mark already. This one is 1 mark. Okay, they are B marks. And if you know that smaller wavelength means greater energy, greater photon energy is B1. Okay, now I think out of the box a bit. I wonder what happens when the electron is not stationary. Okay, so I say that also if the photon were to gain energy, it has to be from the electron, right? So the electron would have to lose some energy. But the electron is already stationary. Electron is like, I got no energy, bro. Electron will have to lose energy, which is not possible because it is stationary. Okay, so this deflected photon must always have less energy. Or you could say, if you want the photon to gain energy, then it has to come from the electron. Electron where got energy? How to give you energy? Not possible. Okay, but this point has to be there. Smaller wavelength, greater photon energy. Okay, so this B1 mark is this one, or you explain this one. So this is the mark scheme. Other sentences mean more or less the same thing. Okay. All right, so that is the photoelectric effect and the de Broglie relationship, which is mainly this one. I didn't do quite a few questions that I will roughly flash in front of you right now. Okay, so questions that I did not do are questions from the past year that looks a bit like this type. You want to find the photon energy and the momentum, okay? And then they randomly got ratio one, like this type, okay? So make sure you can do them. Also, I didn't do or didn't talk much about the experiment because they're not that important. But if you got time, make sure you give them a look-see. The deflection one have come out before one. If you want to try May, June 15, I think we have discussed one and gave another one as homework. Okay, and all this, momentum of the photon, pressure that the light exert on the metal surface. What a weird question. So I will list down questions here. If you already done them, which you should have, then you don't need to worry so much lah. This one, you can try ON19 Paper 43 Question 8. Let me maximize so I can see better. Can try May, June 14, Paper 42 Question 8. The graph one is all over the place, okay? You randomly choose one or two to do lah. Momentum of light, these two would be May, June 15. Paper 41 and paper 42. Question 6. For paper 41 is question 8. Okay, so go and try. Pure de Broglie wavelength questions that probably haven't discussed yet include May, June 20, paper 41, question 11. And also, if you haven't tried the ratio one, go and try lah. May, June 20, paper 42. Question 11B. Okay lah, I think more or less can now. You're good. So go try all of this as part of your revision after this video. Okay, where are we? Okay, so we've done the first third of the quantum chapter. This is a very long saga. We're going to continue with the second part here. I'm just going to draw a 2 here. Did I label 1 just now? Did I? Yes. So this is the photoelectric effect. This is the first section now. The duality section. Photoelectric effect, de Broglie relationship, and how these two is interlinked. Of course, we can ask standalone question or we can link them together. So go and look through the questions. Next one would be application of photoelectric effect and de Broglie equation. Okay, so this includes hydrogen spectrum, hydrogen energy level. I'm not going to do many questions here. Plus band theory. Okay. I would say X-ray is here, but I'm keeping X-ray and CT scan at the medical physics part lah. Okay. So this is where we stop now, right? Right? Am I missing out anything? Hydrogen level, band theory. Yeah, I think that's it. Okay. So the hydrogen spectrum one, you know the continuous energy spectrum. You jump here, jump there. You jump. Okay. So, what do you need to know? You need to know, number one, what is absorption versus emission spectrum? What would you see for an absorption spectrum? You absorb the light away. So absorb the light away. Anyway, all of this is in your notes, okay? So absorb the light, Leoma, absorb energy, so certain wavelength is missing. Emission spectrum, you emit light, so you can see the color line. The color line is this one. Okay, can. All right. So we absorb, when electron absorb energy, it jump up into higher energy level. Pew, pew. Okay. And then emission is already high energy level. I come down. I come down. And then I emit photon. I absorb photon. Important equation that we will use as usual is energy of photon is equal to hc over lambda. So whenever we transition, let's say we transition from 0.85 to 0.34, hc over lambda will be equal to 0.85 negative 0.85 minus negative 3.4. You just take the difference is good enough. It's very obvious in the question or the context of the question whether it's emission or absorption. Okay, so energy of photon is hc over lambda because this one will emit a photon. So you want to find how much energy is emitted. This equation is the one that we use. Make sure you also know how to explain, my friends. Explain the observation. Normally it's 4 marks one. You don't know how to explain, then sad lor. I feel for you, but this one didn't come out in ON20. The last time it came out is May, June 20. Okay, so the past year question notes is already sorted by subtopics lah. So you just find some to do lor. So this is an example of explanation. You can watch the video where we explain thoroughly what happens to the light. The electron in the gas will absorb the energy. All right, electron in the gas will absorb the energy. So that's why there are some missing lines. Because when the electron de-excite, the light is released in all different directions. So you cannot get back the light already. What is gone is gone. So make sure to explain. And then explain discrete energy levels. So always make sure your explanation, right, relate back to discrete energy level. Okay. So this one all look at notes. The second type of question that they can ask you is this type here. Sorry, not this one. This type. Like this one. Or how many possible level of transition? I think this one I record a discussion already. And then if you want to find the maximum kinetic energy, this one is de-Broglie's, not de-Broglie, this is the photoelectric effect. You got work function, you got maximum kinetic energy, you have incident photon. So you know what to do lah. Go and try this question. Okay, so I would suggest if you haven't studied or review, go and try ON18 paper 42 question 11 for this one. And also maybe May, June 17 paper 41 question 11. This one, they are not, the last time it came out properly was ON18. I can't tell the future, so 我不知道 I don't know I also don't know. Okay. The last time it came out in May, June 20 is half a question. Part B, they ask something else. So they just ask you to explain the existence of dark lines. So go figure out how to explain. So the last time the explain came out was May, June 20, paper 4. 4-1. Yeah. That's it. Not a very long topic. Okay. Band theory, even shorter. Because the many distinct energy level was spread out into a band theory. Right. So when it spreads out into a band, the question are all essay. Essay only. Normally is 4 to 5 marks, can be up to 9 marks, but rare lah, rare. If up to 9 marks are actually is quite worth it one because already study ma. Okay, anyway, what you need to know is all in that single page in your notes. I'm going to show you your notes now. Okay, this is your notes lah. This part here. All right. How does temperature affect the resistance of metal? How does temperature affect the resistance of thermistor? How does light intensity affect the resistance of LDR? All the explanation explain using band theory. Okay, so band theory, right? They will ask you things like, how come we got a band? So the reason why we have band is because when the atoms are close together, okay, they will disturb each other's energy level. They push each other's energy level a bit. So the discrete level will spread out and become a band. All right. So for conductors, right, there's an overlap. For semiconductor, there's a gap, but the gap is tiny. So the electron just need a bit of encouragement to push them into the conduction band. For some of your friends, their physics and their conduction band overlap already. They are quite ready for their paper 4. For some of our friends, for some of you watching this, maybe you have a small little gap and you need some push. Okay, lor, go do past year question, go come for AMA, go come for a review session. We give you a bit of energy to push. But if your gap is too big, maybe defer. Give yourself more time to gain more physics to go into the conduction band. Okay, you don't need to know the description, but having this picture in your mind, imagine the electron jumping up will help you explain one. Okay, so let's think about the semiconductor when we jump across the band gap first. Okay, for thermistor, temperature increase. For LDR, light intensity increase. The whole problem here is the electron don't have energy. So you want to give it energy, you increase temperature or you shine some light on it. Because we know when we shine light, the electron can receive it as energy. So electron gains energy, jump into conduction band from valence band. This third point is very important when you talk about band theory. You can't explain band theory without mentioning the structure, conduction band, valence band, forbidden band. Okay, so the electron will jump into the conduction band from the valence band, and if you want to flex like me, you could say across the narrow forbidden band, leaving behind a positively charged hole in the valence band. When the electron go up, there's an emptiness there. It's like when your friend leave you, there's an emptiness there, absence. Okay. So talk about the emptiness. No, talk about the hole. Mention the hole. And then now we got electron. And then we got hole. So we got many charge carrier now. If we have more charge carriers, then the resistance is less. Because there are more particles to help you carry charge. Hence, the thermistor or the LDR, light dependent resistor, are more happy to carry current for you. Okay. For temperature, there's another 6 point. Because some of the students may be thinking, but miss, when you heat up the silicon or the semiconductor, wouldn't all the particle be moving and vibrating and then harder for the electron to move? You are correct. But then the effect of having more electrons to carry charge for you outweighs the effect of having the whole lattice structure shaking. So the resistance still decrease because our problem with semiconductor is we don't even have the electron to begin with. So once we heat up, we now have the electron, so the resistance will drop. This effect is more important than the vibration of the lattice structure. But for conductor, it's not the case. Conductor already have energetic electron. The conduction band is already overlapping with the valence band. So the electron is like, I already got enough energy. I don't need more energy. You give me more energy, it has a negative effect. It causes my whole lattice structure to shake and vibrate. Lattice vibration will hinder the movement of the charge carrier, so resistance increase. So you need to mention when temperature increase, there's more vibration to lattice structure. There's no extra charge carrier. Number of charge carriers doesn't change because the electron inside a conductor are already charge carrier because conduction band and valence band overlap. Okay, so because of the overlapping, you already have. So lattice vibration will only stop the movement, then the resistance will increase. So the past year questions can look like, explain the dependence on light intensity on LDR. Explain why the resistance of a metal at room temperature changes with increasing temperature. So got metal, got LDR, 5 mark. Explain why, unlike copper wire, resistance of semiconductor decreases with increasing temperature, 5 mark. Wow, this one got 7 mark leh. Explain why resistance of a metal increases with temperature. Resistance of LDR decreases with light intensity. Okay lah, I think you see a pattern now. You see this is bonus. Just make sure you write the correct keywords like the name of the bands. Do they overlap? Do they not overlap? And then there's this thing called charge carriers. Okay, so make sure you mention all those things and then explain what happens when we give them more energy. That's it. That's it for quantum. For this entire section, you will expect about 2, I guess. This one I also include X-ray. Let's take out X-ray because I didn't do X-ray here. So I think you will expect about 2 questions instead of 3. Okay. But I include nuclear. Okay lah, never mind. I include nuclear, then can 3 already. Sorry, I take that back. You can get 3 questions because it includes nuclear. So it's still 18 to 24 marks lah. Band theory is 5 to 7 marks. I'll write here for you. Okay, so I got no questions to discuss because they're all very repetitive and we have already recorded quite a lot of examples. Okay, so this one is 5 to 7 marks, closer to 5. This one will be 6 to 8 marks, depending on how much calculation they want you to do lah, and explanation. Okay, can be 4 marks also if they just want you to explain. So that's it for quantum. Okay, photoelectric effect is the more popular one and the more important one. So we expect higher chance for that question to come out. But it doesn't mean that this one won't come out. So make sure you also spend some time. But the good thing is the questions are very repetitive. You do 2 or 3 or you get an idea already. Band theory, you just look at the notes lah before the exam. Make sure you know how to write out the points. Then can already. Cool. Okay, we're going to draw a line and move on to nuclear. Oh yeah, my line not straight this time. Sad. Okay. Anyway, just to metal. Insulator don't need lah. But in case you want to, it's already completed there. Insulator, the forbidden band very big. Electron cannot jump over. Forbidden band too big now. Metal semiconductor. We deal with thermistor LDR. Okay. All right, we're going to move on to chapter 26, where we talk about nuclear. Now, the beautiful thing about nuclear is that there are only 3 types of question. I would say 2 lah, but then Miss Ellie pointed out that I think it's the same type, but actually it's not. Okay, lor. Okay, the first one is our beautiful E equal MC square. So applications of this equation, are there any auxiliary extra equation I need to know? Yes, but not really. I don't know. I mean, I think the mole concept for me is instinctive lah. But I guess if you don't do chemistry, then you need to review your understanding of the mole concept. Because sometimes they will ask you things like, what is the total energy release in this reaction? I think let's say something like that in your trial. I think so lah. Okay, so go ask the mole concept. And also you need to know how to balance equation. No? So these are the things that we assume you know, but maybe it's not good for the lecturer to assume you know. So I tell you now these things that you need to know before you can unlock this one or do a question properly. Because the last thing we want you to do is you not knowing that you need to know this and then you cannot do the question, but you spend some time revising it. That will be a bit sad. Okay. All right. And also our good old EV can go to Joe, Joe can go to EV. This two-way arrow thing is important for small particles, especially in quantum and nuclear. All right, this one is our good old mass defect. So normally, let me choose a different. Let me go and see the ON20 questions. What did you ask? Oh, interesting. Okay, they asked a question that is a fairly different. I think we should discuss this because I know students don't like this. Ta-da! Look at all the lines, Cher. Look at all the lines. Well, we gotta ask you to explain something, right, in the paper. So why not this one? So this will be ON20 paper 42 question 12. All right. So here, the things that you need to define besides a mass defect, I will list down the definition you need to know. As exercise, you should go and find them in your notes lah. Then you write down again law in the list. Help you memorize also ma. I remember what's the point. Binding energy, mass defect. I think that's it lah. So define nuclear binding energy, 2 marks, and then explain what is meant by a fission reaction. Okay, so binding energy, think of the nucleus. Proton and proton, they don't like to stay close to each other. They're like, bruh, you positive, I positive. I don't like you. Why are you so close? Hello. So there's actually work done to bring the proton close to each other. But if you want to separate them to infinity, you need to do work. So this will be the energy required to separate to infinity all the nucleons in a nucleus. Okay, we see a nucleus and we go like, I'm gonna separate all of you, protons and neutrons away. Okay, nuclear fission reaction brings us to the next concept that we need to know besides binding energy. So this energy here is the energy of the reaction whenever there's a change in mass. So for binding energy, we will write something like, let's say carbon 12. Carbon 12 consists of 6 proton plus 6 neutron. So this is what I mean by you need to know how to balance the equation. Okay. So normally they will give you a table 1 mark, correct? So they'll give you some numbers and then you calculate the mass defect. So the mass defect here would be 6 times the mass of proton plus 6 times the mass of neutron, the product of the reaction minus the reactant, which is the mass of carbon nucleus. Nucleus, not atom. So you will get something here. And the next conversion that you need to know is how to go from U to kg or kg back to U. So go back to your question paper. Let's say you look at this one, your question paper. Go back to page 1. I see you. You see me? See the U here? Unified atomic mass unit. 1.66 times 10 to the power negative 27 kg. Okay? So you should know that 1U is 1.66 times 10 to the power negative 27 kg. I see you. You see me. Please go and look and use the paper to help you so that your brain doesn't have to carry so many things. Let's move on. Next. So here you will have something, maybe in terms of U, you have to convert to kg. Maybe you don't want to convert to kg. If you don't want to convert to kg, okay, then you should know the proof of E is equal to 1 UC square, which is equal to 934 mega evolt. Okay. I write everything for you lah. This proof came out in your trial already, so it shouldn't be a problem. If got problem, review the trial discussion video. Okay. Just fast forward to the side and just watch that few minutes. All right. So you should be able to find the mass defect and then slot this mass defect into the equation. E is equal to delta MC square. So plug it into this thing here. Okay. Then you can find how much energy is needed to separate to infinity all these 6 proton and all these 6 neutron. So a carbon atom sat on the wall, a carbon atom had a great fall. So all the king horses and all the king's men could not put proton and neutron together again. Separate to infinity or the binding end, which is the binding energy. So you find lah what's the difference and then you calculate this one. If we repeat this process for every single thing on the big periodic table, we go get this graph. Let's say take binding energy per nucleon number. So this is BE. And then let's say you want binding energy per nucleon number, then BE over 12, because the nucleon number is 12, so just BE over A, okay? This is A, nucleon number. So you're going to get a graph that looks a bit like this. I know there are some zigzag one, but I don't care about those. That one, we leave it to the chemistry people. What we care about is this magic number, 56. Everybody wants to be 56, okay? So here, anything that is smaller than 56 will undergo this process called fusion. Fuse together, become big. Everything that is bigger than 56 will undergo fission. Break apart, become smaller. Everybody wants to be 56. This is iron. That's why the earth is made out of iron. That's why you go Minecraft mining. What's the most important thing to have? Iron. You think it's diamond? You think it's gold? No, it's iron. Okay, anyway, what is meant by nuclear fission then? Well, my friends, nuclear fission is when big nucleus becomes small nucleus to become more, in the effort of becoming more stable. So here we will say that a large nucleus divides or splits to form a smaller nuclei. So got more than one lah, separate into two ma. And then they expect you to write extra things. And in the spirit of full disclosure, because you also want to graduate already lah, I feel that it's like they just say you write anything that you think is related, which I think is a bit sus lah, because why though? Okay, anyway, just write a bit more. Either it's initiated by neutron bombardment, or let's say I'm the student that is like, I don't want to write so much, then form smaller nuclei of approximately the same size. I mean, I am that person that likes to write less lah. Okay. Or you could say the binding energy per nucleon increases. So I'm going to comment on each statement here. Initiated by neutron bombardment, this is uranium reaction. Okay, go and look at your notes. Resulting nuclei of similar size, which is generally what happens. Binding energy per nucleon increases. This means the product is more stable. But do not write product is more stable. You will remember this point because you know that all chemical reaction has to achieve stability. So these two, product is more stable. Neutrons release, yes, most of the time it does. So think about again your uranium-235 reaction. The combined mass of smaller nuclei is less than the mass of mass nuclei. So again, it points towards the product being more stable. But you see, they don't allow you to write this sentence. The product is more stable. How do you know? How you know? How do we know? Or how can we tell? All this, no? Any one point can already. Okay? So just write a bit more. Okay, last part. I'm going to keep that thing there. Repaste the question again. Okay, a student suggests that one possible nuclear reaction is this one. Okay, so I see the neutron bombardment. I see somewhat similar size, but sure. The binding energy per nucleon of a nucleus varies with the nucleon number, of course. Use this variation to explain why the reaction would not result in an overall release of energy. 3 marks. Hmm. Remember I said everybody wants to be iron? Don't you think iron also wants to be iron? Or is iron having an identity crisis? 56 is at the peak of the graph. It is the most stable element. Everybody wants to be it. Okay? So you can say, nah, this graph, the peak here is 56 leh. Everybody wants to be 56. So you can say the binding energy per nucleon is maximum at around or at exactly nucleon number, or A is equal to 56. So if this 56 split into smaller one, so I don't know where this is, but let's say this is 37 and let's say this is 20, you see these two so not stable. No, it won't happen. Everybody wants to be stable. You also want to be stable lah, if can, correct? No, I mean I like to live life dangerously. Life is dangerous enough. You don't need to seek instability, okay? So here you can say that the products of the splitting, the products of this splitting Fe56 nucleus has lower binding energy. The stability is less, okay? So reaction would require input of energy. Naturally, it will not occur. Of course, if you go and disturb the iron and you heat up the iron, then it can happen. Sure, give it energy. Naturally, it won't happen. It won't happen. It doesn't happen easily, and it won't release energy. So it's not like the uranium-235 where the decay is so random and we kind of like don't want to wait so long, so we just whack it with a neutron to make it happen. But when it happens, it will give out a lot of energy. So anything that goes away from stability will need you to put energy in. So the reaction will require some input of energy. Okay, I think I've forgotten the keyword here. Lower total binding energy. Okay, so I think in the video that we've recorded, we got explained a lot about how the binding energy talks about the stability. So if the total binding energy is less, it means that it is less stable. That means that when you go from here to here, this energy actually is less. Lower total binding energy, less stable. So if that is the case, right, then what will happen is I need to put in energy to force the nucleus to decay. The nucleus is already stable, high binding energy. So we need to give it energy so that it's forced to split, but it doesn't like one. So when you go to here, energy needed, absorbed. Or in the chemistry word, we call this what? Endothermic. Okay, so from here to here, energy is absorbed. And then just to draw a different graph here, energy is released most of the time. The best way to know whether energy is released or absorbed is to look at the mass defect. Here, generally, student want like a very quick answer, but there's no quick answer. It's a reaction by reaction basis. There's a general trend, but there are exceptions. So the general idea is if your mass defect shows an increase in mass, you got extra mass. Where the extra mass come from? Energy is absorbed. Okay. If your mass defect decrease, and you lose energy, you lose mass liao. Why? Because energy release. Okay. So this is the only way to actually tell. Another way to tell is to talk about stability. If something is more stable, it means that the nucleus is releasing energy. It's a very simplified way of talking about it, but it's sufficient enough to answer A-level question and at this point in time in your exam. Okay. So whenever all this fusion, everybody wants to be iron. Energy release. If you go against nature and you want iron to decay, iron will reluctantly decay for you, but it is going to want to absorb some energy as a price. Okay? Energy absorb. In this direction. So this is the golden band. You want to leave the golden band, you need to absorb energy. It's having a good time there, doesn't want to leave. All right. So this is the slightly different version of using E equal to mc square, where they talk about the binding energy. Okay. So binding energy tells us about the stability. Maximum at A equal to 56. The product will have less binding energy. So less stable, reaction will need input of energy to force it to happen. So that is the first type of question. Either they ask you to calculate where they give you tables. Okay. Don't worry about the OneNote. I'm going to send it to you. Table that look like this. You balance the equation one. I set one in the trial paper before, but you can see there are so many. You see a table, you can try already. Okay. You see a table, you can try all this binding energy per nucleon. All right. And if you really want to understand why we can use binding energy, this one came out in your trials, remember? Yeah. Okay. And then after that, there's a mole concept here. So maybe you can either redo this or do part C and D that I didn't ask, or is it part D only? So if you want to do in combination of the mole concept, this will be, okay, I will suggest some question to do. ON19 paper 41 question 12. I throw the window here, I throw the window there, I cannot see all my windows. Part D. Okay, if you are interested in this calculation, part C, I will slot it. You just tell me I send you the OneNote. Just ping me, okay? I'll put it inside the topic in your library, but it's a lot of chemistry and combining chemical equation is not needed. So you can just choose to memorize the method. Unless you just want to know then don't worry. You want to know, just ping us. We will send you the question. Took me a while to balance that equation because I don't like to balance equations. I mean, I don't mind if it's maths, but chemistry one, I need to make sure all the number the same, like doing accounting like that. There are not many. Okay, another one that you can try regarding the balancing the chemical equation, etc. May June 17 paper 42. I don't remember what we have recorded. If we have recorded some of this, then we'll find something that is more similar. whether the energy transform or not. 42, 41. The mole concept one is fairly rare lah. So I think this is the only one in recent years. Okay, so we're gonna carry on. Let's see if I can finish this by 5. So the video is not more than 2 hours or 2 hours plus. If not, nobody ain't gonna watch this. Alright, so the last one, which is type 2, type 3. Okay, the first one there is graph. Graph of radioactivity. Okay. The second type, the third type one there is calculation. Calculation of radioactivity. Okay, let's talk about side dishes first. Things you need to know before you want to try to answer. So this one is more straightforward. Mole concept, balanced chemical equation, basic conversion. What you need to know here, you need to know how to deal with a log-log equation. If you don't know, then physics is going to be tough on you, my friend. I repeat, if you don't know how to log-log, physics 很辛苦 one, very tough. Can you please watch the mathematics video that Miss Ellie so helpfully recorded for you if you need it, to make sure that when you see an equation like this in your formula sheet, you understand what it means and you know how to use it. If not, it's just going to be pain, just pain town when it comes out. Why it comes out in paper 5 and then come out in paper 4 radioactivity and then come out in X-ray? You sad lor, very sad. Don't do this to yourself. Learn a bit, no need to learn a lot. It's not going to be like maths. You just need to memorize the general form of the equation. Okay. Well, I paste this equation by one note hang. Okay, I shall continue. Don't care. Okay, stop hanging already. Great. So graph of radioactivity. Doing this equation, we're going to use half-life. I will normally just draw a flow chart to link up all the equations that we need to know this part lah, because technically speaking, if you don't need to know the proof, then no save time lah. So what we need is N is equal to N naught E negative lambda T, and somewhere across the world we have A is equal to A naught E negative lambda T. Okay, they are related by the fact that activity A is equal to dN over dt. Let me zoom in a bit. Okay, so let's name these things in case you see this and then you don't know what they mean. This one is activity at time t. I don't know lah, 2 year, 3 hour, whatever lah. Okay, this A naught is initial activity. What is activity, miss? Number of decay per unit time. Rate of decay. How many nucleus will decay in 1 second? It's a bit like number of students scanning their face in a given time in MCKL front gate. The student DT. Number of nucleus that go through that reaction in a given time. Anytime lah. Maybe the D student DT is very high at 8 a.m. but super low at 8 p.m. Okay, so it's time dependent. N here stands for number of nucleus. So this is number of undecayed, not yet decay yet, not yet have reaction yet. Number of undecayed nucleus at T, time T. Okay, time T is here. This N naught is the initial number of undecayed nucleus. Okay, so whenever I study physics or maths, I always ask myself, what are the constants that I need to know so that I can use the equation properly? All right, so I need to know the initial conditions. If I don't know the initial conditions, it's very hard for me to do anything. But sometimes they can give you 20% of the nucleus already decay. The activity decreases by 25%. So it is also indicative of the initial activity, because then they are talking about ratio. A over A naught is 25%, N over N naught is 90%, whatever lah. So it can be either a percentage or they tell you what the initial value is. So what you need to know before or hunt for in the question is number one, either initial conditions, which is A naught or N naught, more common, but less common would be some form of percentage change or ratio. Find the time taken for the number of undecayed nucleus to decrease to 1/3 its original value. Statements like this. Okay, percentage change or ratio change. Number two, you must know lambda. Lambda, 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 lambda. Not wavelength. Hello. We talk about a lot of lambdas in the first 1 hour of this recording. Those lambdas are wavelength. No other symbol to use there. Sorry, kid. This lambda is called decay constant because it's named by physics people and we don't have brain space to give it a posh name. Okay, decay constant. Decay constant can be calculated here. Saw or not? 0.693 over half-life. Forget, go back to front page, use it. Use the help that you can get. But, and I say this, I don't know, is it important to you or not? But this one, you need to know the proof. How to show that lambda is ln 2 over half-life, 0.693 is ln 2, or how to show that half-life is ln 2 over lambda. Okay? So a side note about lambda and t. Lambda and t can have what I like to call inverse units. Miss, what means? Well, you see, your e to the power of negative lambda t, maybe this lambda is, maybe your half-life is 2 days. So you go 0.693 divided by 2 days. Can. If your time t, let's say, is 10 days, then can. Days and days, 1 over day, multiply by day, the day and day, bye-bye. No more days. No more days to paper 4. Bye-bye. Okay, so days can cancel, then can. If you are like very confused, then you just change everybody to SI, then confirm correct, but your penalty here is time. So it's either you develop a sensitivity towards units and know when to convert and when no need to convert, or you go like, never mind lah, miss, I got time. Then you slowly convert the time. Okay, so you can change this t to second lambda, but if not, then you don't have to. This is what I mean by familiarity with the equation. If you're unfamiliar with the equation, how are you going to use it? You can't use it properly, right? Then here wrong, there wrong, physics very hard. I'm so sorry, boy. We need to learn to use the equation. Okay, so this one is 1. Ln 2 over half-life is another version. Lambda is also ln 2 over half-life. Okay, so what are the definitions that you need to know? I'm going to write at the side. Definition. Number 1, activity. A is equal to dN over dt. This unit is called becquerel. I'm pretty sure, BQ, you know how to write this in sentence, right? Activity is rate of nuclear decay. Okay. Number 2, what you need to know is the definition of lambda. No, not lambda. Lambda, yes. Lambda should be defined as dN over N over dt. Go watch my video. I got explained very thoroughly. But this, in short form, just to recall for exam purposes, this is probability of decay per unit time. I explained very long-winded in the video, so you can go and watch. Okay, okay. Or you just memorize probability, dN dt, probability per decay per unit time. There are some slightly annoying questions, I like to call it, because they are more mathematics than they are physics. But I guess Cambridge is just a troll some days, okay? So for questions where you absolutely need to know the decay law, if you don't know, then you cannot answer is May-June 19 paper 41 question 12A. Only came out twice. The first time I saw the question, I laughed and laughed because I was like, who and how and am I doing calculus now? But then I guess can lah. Okay, in the recording, Miss Ellie has recorded this one, May-June 15 paper 41 question 9. If you haven't watched it, haven't done it, go do. Okay, so this one, you really need to know what on earth we're talking about lambda, what is dn, dt. We need to know some first principle of calculus lah. Just go watch the video, okay? All right, and then the third definition you need to know is half-life. Half-life, T half. Time taken for the total number of activity to decrease by half, or time taken for the total number of undecayed nucleus to decrease by half. Time taken for activity to decrease by half its original or initial value. All right, so these are definitions that you need to know. You can go and try out these two questions. It's just solely based on the definition. Okay. If you don't know the initial condition, you don't know lambda, you cannot use the equation. So please make sure you can find them from the calculation itself. And other thing you also need to know here is the mole concept. Okay, then if you don't know how to do mole concept, this chapter can be a bit challenging, especially if you don't do physics. I mean, sorry, don't do physics while you're here. Chemistry, if you don't do chemistry, no chemistry, then this part, we need some time. Okay, lor, that's all. We're going to do some question on both class. One is the graph only, one is the calculation only. Okay, to round off the day. Like that. That's all. No more now. A is dn dt, but A is also equal to lambda n. Actually, this one is more useful. Why? Yeah, because this is exponent. You differentiate exponent, you get back exponent with a constant in front. So I throw the constant in front. Watch video again. You differentiate this one, don't you get this one? Exponent is a very special cookie. You differentiate exponent, you get back exponent. Differentiate exponent again, you get back the exponent. Only thing different, the change is the constant in front. So A naught will be equal to, see the lambda here, lambda come down, lambda n. Okay. This lambda differentiate, go down, lambda n. So then A naught will be lambda n naught and A is lambda n. Yeah. Only for exponents, this one work. Okay, let's try some questions. I'm going to also do the ON1. ON20 paper 41, question 12. Okay, we have iodine 131. This is the calculation one. It doesn't have graph. Okay, later we'll do one with graph. In my opinion, the graph one and this one is the same, but Miss Ellie also pointed out that not every student see equation and think of graph. I'm like, okay, so I will see them as separate law. All right, so here, I'm gonna put this one here. Okay, so iodine 131 is a radioactive isotope with a decay constant of 1.9. Oh, this is very nice. They have this in SI for me. I'm happy and satisfied. This is my lambda. State what is meant by radioactive and decay constant. So not the song Radioactive by Imagine Dragons. You can write the lyrics here, but you won't get marks. Okay, radioactive is when a nucleus decay, right? So we start, what happens, what do we start with? We start with an unstable nucleus. Okay. Decaying spontaneously. Oh, I've forgotten one thing. Let me scroll up and add it into the notes. Extra things you need to know. I write here. What is spontaneous? What is random? Okay, it's in your notes. Spontaneous means you don't know when it will happen. Your friend is very spontaneous one. Maybe call you at 2 a.m. for MACD before MCO lah. Okay, spontaneous. Random is you don't know which one will decay. Every particle will have the same amount of decay time and it's not dependent on the condition. Okay, go look at the notes. Okay, so decaying spontaneously, okay, emitting radioactive particles such as alpha, gamma, alpha, beta, and gamma. Okay. Any combination of alpha, gamma, and beta, or any single one of them. Okay, hang on. In case this is the only time you had to look at this, we help you a bit by finding the notes and cropping it in. Okay, so spontaneous and random. At least because, you know, if I'm a student, right, equation I can do, but these kind of things I may not remember. So when I need to think about it, I should immediately be able to recall it. So I spend some time going dig long. So you should know why it's spontaneous, not affected by external factors. Okay, and random. Random for me, I think of probability because I also, well, what did I do? I also did maths. So I think of probability. Okay, so random here means we cannot tell which nucleus will decay next, and the constant probability that a nucleus will decay. All right, moving on. Decay constant here. Decay constant, you will use back that definition that I've given to you, which is probability of decay per unit time. So this will be probability of decay of a nucleus per unit time. Guys, 2 mark is 4 mark. You want to throw? Don't throw, man. It's good marks. Keep it. Don't just leave empty. Or don't simply write anything. This is definition. You must write it in a certain way, okay? So radioactive is when unstable nucleus decaying spontaneously to emit radioactive particles such as alpha, beta, gamma. We went through this in AS before, okay? And decay constant is all about probability per unit time. But you should mention probability of decay lah, of a nucleus. All right. Some water becomes contaminated with iodine 131. Hiya. The activity of iodine 131 in 1 kg of water is 560 becquerel. This means every second I will get 560 nucleus of iodine decaying. This is what this number means. 1 second, 560 particle decay. Another second, another 560 decay. Determine the number of iodine 131 atom in 1 kg of water. So this is what I mean by using the equation and also thinking about particles. Okay, so I have activity. Do I have activity? This is activity. I want to find N. A is lambda N. So this one is 560. Do we have lambda? Miss God, remember? This one, 9.9 times 10 to the power of 7, negative 7, I mean. 9.9 times 10 to the power of negative 7 times N. So we can press our calculator and we'll find that N is 5.7 times 10 to the power of 8. So we have this many iodine nucleus inside my 1 kg of water. Okay. Now, whenever you use this equation, because this unit is in becquerel, then this one must be second negative 1. Scared forget. Right back up here. This is how you do revision. You have a frame of your notes, and then as you do more past year questions, you go like, oh yeah, I didn't take note of that. So come back here and write lor. This one is in becquerel. This one is second negative 1. The inverse unit thing can only use when it lies inside the exponent. Again, if you are not sure, change everything to second. Confirm correct one. Just more time. All right. So we got A lambda n and got this. So regulations require the activity of 131 to be less than 170. Calculate the time in days for the activity to be reduced to this much. Okay. So in my brain, I already see a graph. This is my graph. Activity and time. In the beginning, this is 560. Activity in becquerel, this is 560. So eventually I need it to drop to 170. If not, Shabazz cannot open the water pipe. You and I know water. We use 1 cup of water to brush teeth. Selangor always know water one, in case people you don't know. Very sad. So we need to go down to 170 before we can use it. So I look at this graph, I know the equation A is A naught E negative lambda T. So I'm going to use A is A naught E negative lambda T. I got explained in the video how to modify from this given, from this one. Okay, this X can put A, can put N. This X. And this one, and this one, there, this one, or this one, Okay. So anyway, we're gonna use it now. We have the initial conditions is 560. E negative, we have lambda. Lambda was given to us 9.9 times 10 to the power negative 7. We're looking for time. And this one is 170. So you bring the 560 over, you already will see some sort of ratio, which is what I'm talking about. Have some ratio. Okay. Nah, I teach people how to press calculator some days. So today is the day lah. 170 divided by 560. Okay, so this one you bring over already. Depending on your appetite, I am the type where I can continue pressing, but if you scared or you don't want to, you can just copy 30357 is e to the power of negative 9.9. This is especially important if you are not familiar with exponent to take your time. Exponent is about to transfer over. You transfer the exponent over and put here. This one become ln. Okay, so now ln 0.30357 is equal to negative 9.9 times 10 to the power negative 7t. Okay, so what I'm going to press, because this one is already my answer, I can just press ln answer. Okay, divide by this 9.9. So divide, paranoid, then put bracket law, 9.9 e. So this is times 10 to the power of negative 7. Close bracket, press equal. Okay, so this one, where are? Oh, there's a negative there. Okay, so 1204, I think calculator died, but this t would be 1204, so 1.2 lah, times 10 to the power of 6 seconds. You will do yourself a great disservice if you didn't notice the day here. How long we need to wait? Shabazz, I want my water. Days. Please make sure to convert this. So how to convert to days? 1 day, 24 hours. 1 hour, 3600 days. Okay, so if you do that, it's around 14 days. So we won't have water for 14 days lah. We'll go and contaminate the water source. Hello, excuse me, please. Don't do this. I would like to shower. Okay, so please, if you're not familiar with pressing, just go do. There are plenty of questions that you can try in the past year topical selection. From difficult to hard one. I think you can go and look at the task list lah. Quite many. But if you want me to casually choose, if I don't choose, you don't do. Although I don't understand why you do this to me and yourself. Why? Hang on. I will try to choose some. Again, I don't know whether recorded or not lah, huh? So if already recorded, you choose other stuff lah, or you haven't tried yet. So go and try ON19 paper 42 question 12, similar stuff. This one got ratio one, okay? And finally, let me give you another one to do something with some moles in it. Some moles. More iodine and blood. Okay, can. Then you do this one lah. ON17 paper 42 question 12. This one got iodine in blood. Sometimes we inject iodine in blood because we want to measure the volume of the blood of the patient, or we actually are performing some form of chemotherapy lah. So we want to see whether the chemo is still inside your body or not. So the iodine is used as a not that harmful marker, because beta particle is not that harmful. Okay, so one last one that has graphs. And okay, I want to do one that doesn't have some. Let me check which one have we recorded so we don't repeat that much. So the graph didn't come out last year. Again, I'm not saying it will come out this year. I just said it didn't come out last year. Wrong. Okay, we already recorded page 28 and 24. So this means I can do this one. May, June 18, paper 41 question. Yes, I think this one no recorded now, but I could be wrong. Doesn't matter. Graph. Technitium. So this is a half-life graph that I say I visualize in my head, but sure, doesn't matter if you don't. State what is meant by radioactive decay. State already is here. How nice. How nice. Nah. Okay, so unstable nucleus decaying spontaneously, emitting radioactive particles such as alpha, beta, gamma. All right, here we have the number. Okay, means this one N-t can. N and T, A and T, same shape, different values on the y-axis, but same shape. Okay, so here determine the activity at 14 minutes. Show your working. Hiya. Okay, let's go and find 14 minutes first. 14 minutes is 1, 2, 3, 4. Is this 14? No, 5, 6, 7, 8. 14 is here. No, wait, this is 14, 14, 15, 16, 17, 18. Yep, this is 14. So 14 is here. Wait, think of the definition of activity. Activity is dN over dt, which happens to be the gradient of the N-t graph. The ability to draw a tangent line and to find the gradient of a tangent is very important for physics, okay? If you cannot draw a tangent line, then your life is quite hard lah. But also, my life is also quite hard because I don't know how to draw it on OneNote. So I am just going to try my best here. Judging by eye. Is it tangent enough? Superman. I think, I mean, I'm not like, it's not perfect, but I think can lah. Something like this. So it should just touch the curve at that point, and my line is kind of thick. So cannot, but let me adjust this a bit. So I would tilt the line a bit lah, but you know, I'm limited by OneNote. So this is 4 marks. You need to draw the tangent line. You need to draw the triangle. You need to find the gradient. Okay. So in the interest of saving time, I'm going to fast forward this and jump to my good friend, Mark Scheme. You don't do this, because you are sitting for exam. You better make sure you practice first. Draw the tangent line, draw the triangle, show the working, and then only double check the range. That's my suggestion. It's like this. Correct tangent drawn at 40 minutes. Magnitude of gradient identified as activity. So you can see this is my C1 mark here. This is the C1. Correct working for gradient. Okay, I got draw tangent line. So this is C1. I find gradient, something minus something equal to activity. And then finally, activity equal to 3.6 times 10 to the power of 4. Okay, so this one is C1. This is A1. Is it C? Yes, all right. So this is one method. You can draw a tangent line. So if I'm going to use this line, let's see if I can get the answer or not. I will choose a coordinate that looks like it passes through the corner, like here. Okay, so remember we say corner plots only. I also tend to read corner plots only because if not, then very hard, Okay, this one looks fairly corner to me. Not exactly, but close enough. So this coordinate here, down here is 25, 2.0. Coordinate up here is 2, 4, 6, 2, 2, 4, 6, 7. Yeah. No. What am I doing? 1, 2, 3. 3.5. My bad. 3.5, 2, 4, 6, 8, 10. This is 5. So 1, 2, 3. Correct, 3.5. Then here would be 2, 4, 6, 6.6. Okay. I just continue here and check my answer. 25 minus 3.5 minute. So needs to convert because they want becquerel. This is SI. Minute have to convert to second. So this one times 60. Okay, on top here, what do we have? 3.5? No. 6.6. 6.6. Or rather, 2.0 minus 6.6 times 10 to the power of 7. See, there's a prefix here. It's a negative gradient, so I don't expect anything else. Let me press my calculator. So 2.0 minus 6.6. 1E7 divided by 25 minus 3.5 by 60. Okay, so what I got is negative 3.565857. 1, 2, 3, 4 times 10 to the power of 4. Okay, so the magnitude, this one, there's a negative here. I also got explain the video why there's a negative, because the rate is decreasing. Okay, so you can put negative gradient or you could just opt to choose the value at the end. So this is my gradient, which is this one. Then you can put hence A is equal to 3.57 times 10 to the power of 4 becquerel. Proven. So the gradient is equal to this one. You add a negative in front if it makes you happy. I put back the negative here. This one will be positive. Negative gradient because the rate is decaying, dropping. Okay, or we take the magnitude only. So please remember to convert to SI. You go convert to SI. You go convert to SI. This one all okay. Then this one is C1. Okay, and then finally this one is A1. So normally when you draw a tangent line, it's quite worth it one, but it will take you some time. You draw a tangent, then you go and find the value. Okay. So some of the students may be thinking, is there another way, miss? Because I don't like to find tangent and I always don't know how to draw tangent. Tip to draw the tangent is the gap between the lines should look fairly balanced and even. So the gap between the curve and the line that you draw. Okay, it takes practice. Another alternative method that they allow is for you to take the reading. Okay, so we are still going to start with A is equal to dn dt. I'm going to park the mark scheme here, okay? So that I can use this empty space. A is equal to dn dt. But from here, I can say A is also equal to lambda n. So at t is equal to 14 minutes, I can find lambda. We cannot use this for gravitational potential if you're thinking about your trial sidebar because there's no such relationship for gravitational potential, okay? So here, we can read off this reading, dot, 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 and I read this reading. It looks like 4.2, 4.4 times 10 to the power of 7. So this lambda is 4.4 times 10 to the power of 7. Okay. Can we find lambda? We need to find lambda, right? So think about substituting. We got, hey, wait, this is not lambda, sorry. This is n from the graph. It's time to stop now. Beginning to make mistakes. So this n is 4.4 when t is 14 minutes. You can substitute n, but we need to find lambda. Let's finish up this one. Find lambda first, then we can find activity. Lambda is ln 2 over half-life. We need to go and find out what half-life is. Okay, what did we start with? We start with 8.2468. Oh, Chinese number. We like 8.8. 8.8 dropped to 4.4. Wow, coincidence. This also happens to be half-life. Okay, because we dropped to 4.4. 8.8 dropped to 4.4. Half-life. Time taken for it to go down by half. Is it? No. This is 8.824. Yeah, 4.4. Okay, so half-life will be ln 2 over 14 minutes. Miss have to convert. Yes, remember? Previous example already mentioned when we use this beautiful equation. Why change highlighter? When we use this beautiful equation, everybody got to be SI. So this will be ln 2 over 14 times 60. Now we can substitute. You can press this one now also can, but I prefer put everything inside. So A will be equal to ln 2 over 14 times 60 bracket 4.4 times 10 to the power of 7. And then I will get 3.6 times 10 to the power of 4. Or, okay, 1 mark. You write A is equal to lambda n. And you know at t equal to 14, this is C1. The initial substituting condition is C1. Second mark, you find the half-life, C1. Third mark, lambda is ln 2 over half-life. Yeah, lambda is ln 2 over half-life. Fourth mark is bringing it all together. Of course, if you skip this step, you're right here, we can also see ln 2 over half-life. So this one is also okay. 1, 2, 3, 4. Which one is nicer? Up to you. Okay, without calculating the half-life, Sure. Use your answer in 1 to determine the decay constant. Oh, so you can see, right, their intention is actually for you to use this method. Later on in the mark scheme, maybe many examiners see many students do it this way, then they have a feeling of compassion and empathy, so they add it in. Okay, but right now, without calculating the half-life, you need to go and find the decay constant. Okay, so we're going to use A is lambda n. So that means do not use half-life is ln 2 over lambda, or lambda is ln 2 over half-life. Don't use this. So find lambda. My answer in 1 is 3.6 times 10 to the power of 4. Or if I use my graph, okay, I'm going to use the graph one. 3.57 times 10 to the power of 4. We're looking for lambda. What's the number of particle at 14 minutes? 4.4 times 10 to the power of 7. Then you can find lambda, which is 8.2 times 10 to the power of -4 second -1. That's why the working looks so K-ing. K-ing looks so weird lah, because it's like, we use the same thing 2 times. Why ah? Because their intention is for you to find the tangent line. But maybe too many students did the anomalous method like this, and then they're like, okay lah, we give mark lah. But actually, this is the gold standard. This one, do this. Look at the gradient. This is what they want. Then your working flow will make sense. You find the gradient, and then you find the lambda. But we shortcut this one by looking for half-life to find lambda. So there are 2 ways to find lambda. This is the slightly longer way. You find the activity or the gradient of the tangent line at a given time, and then use A equal to lambda n to substitute with n. So this is what we mean by graph. So there are certain graphs where they will ask you to find half-life, but in this case, they were very straightforward. They say without calculating half-life. So don't risk it. Okay. This part here, if you look at the examiner's report regarding drawing the tangent line, okay, so please learn to draw tangent line. Line from origin to the curve is not a tangent line. Okay, so the easiest way, in their opinion, or the way that they prefer, is to draw tangent at 14 minutes. Okay, so drawing tangent is throughout your A2 syllabus or your paper 4. Drawing a tangent line, whenever there's a differential relationship, whether it's dn dt or deflux dt, that one is quite rare lah, or df dr, potential gradient, the skill of drawing a tangent line is as important as the skill of navigating a log-lon equation, as important as the skill of linearizing your equation, as you can tell from the previous question that we did here. Linearizing. These are very important skills that you should know. If you don't know, you have some time to brush up, so please do so. Okay, so I think that's it for nuclear physics. In a nutshell, we either have the binding energy style question, which I have some suggested ones that you can do here. And we also have the whole idea of radioactivity and decay law. Go and spam past year questions. There are some suggested one that I put here and here. The graph one, you just flip past here lah. You see a graph, you do lah. That's all. They all look the same. Okay? Can take some initiative. You want the A, go and earn it. Okay? Now, see this graph? What's so weird one? I actually recorded this one already. Go and watch the recording. Okay? And then there are not many graphing questions. Like that one. Not many already. Okay? So the more popular one is the calculate ones. So go do a few to level up your experience. All right. So that's the end of the recording.